Hello, this is Professor Kernler again, and in this video, this is our last one in section 17.6, talking about surface integrals. We're going to talk about two main ideas in this one. First is what if our surface is given to us explicitly, where z is a function of x and y. And then second is, what about vector fields? So suppose we have some field and we want to integrate over that surface, what that might mean. And we'll talk about that and do a couple of examples of that. So first, what happens if we have an explicitly defined surface where z is some function of x and y? Well, we can still do that parametrically. It's just a little redundant. You can just use u as x and v as y. So the tangent, the t in the u direction would just be the tangent in the x direction, which would just be 1. It would be x. So in the x direction, x is increasing, y is fixed. So you can think of it, this is a bad example, or a bad form here, but you can think of it as x, 0, and z. So when x is increasing, when y is, actually y is just fixed, y is some constant. So then in the x direction, the derivative would be 1, the y direction would be 0, and then in the partial derivative of z in the x direction would be z sub x. So that would be the tangent vector in the x direction. Similarly, for v, that would be the tangent in the y direction. That would be 0, 1, zy. The normal vector would then be the cross product of those. Didn't really leave enough space here. That's I, j, k, 1, 0, zx, 0, 1, zy. So that would be, let's see, negative zxi, and then minus j would be negative zyj, and then k would just be 1. And the magnitude then would be the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1. So what we can end up with then is evaluating a surface integral of a function that's explicitly defined. All right, so the surface integral would be the double integral over the surface of f of x, y, z ds would be the double integral over the region of f of x, y, g of xy, right? This is where the surface z is given to us as a function of x and y. And then the magnitude would be, that was the zx squared plus zy squared plus 1 dA. And the dA in this case, right, that's usually in our parametric UV plane. In this case, that would just be in the xy plane. All right, so let's look at an example here. I want to find the mass of the surface lamina. What that means is you have some surface, there's some surface here, and it has some kind of thickness to it. So it's like a plate, but here it's not. In Calc 2 you sometimes do these depending if your instructor did those or not, but you have this plate that's in the xy plane. Well, now ours can be a surface. It's a three-dimensional surface, and we can find its mass. So ours is the first octant portion. I think I may have stretched out the wrong one there. That's fine. Well, x, y, z of this plane, x plus 2y plus 3z equals 6. We're going to assume the density is rho of x, y, z is x squared plus y squared. That's our density. So for the mass, we're just going to integrate the mass over the surface, not the volume, not a region. It's this mass is the density per square unit. Okay, so we need to, let's graph that. Let's see, when y and z are 0, x is 6. When x and z are 0, y is 3. And then when x and y are 0, z is 2. So we have this little portion of the plane that we're looking at. It's just the portion in the first octant. The mass will be the double integral over the region of our rho function times the square root of the partial derivative of z with respect to x plus the partial derivative of z with respect to y plus 1 dA. Okay, so we need to find what the region is in the xy plane. Let's take a look at that. X, y. We have 6 crosses the y-axis at 3, and we have this region. So if we want to draw the graph of that, or let's see, what would that be? That would be, well, I guess we could just do when z is 0, right? So x plus 2y equals 6. We could just do the trace in the xy plane. Otherwise, you could solve this here and get y equals negative 1/2 x plus 3. Right, starts at 3, slope is negative 1/2. Either way. Okay, so let's see here. This will be, oh, we need to get those partial derivatives, don't we? Okay, so let me go down, get some more space here. X plus 2y plus 3z equals 6. We need to get z explicitly as a function of x and y. 3z equals negative x minus 2y plus 6. Z equals negative 1/3 x minus 2/3 y plus 2. Okay, so the partial derivative of z with respect to x is negative 1/3. The partial derivative of z with respect to y is negative 2/3. Right, so let's go back to our double integral. We have our rho function, x squared plus y squared, square root of negative 1/3 squared plus negative 2/3 squared plus 1. And let's just do dy dx. And y will go from 0 up to negative 1/2 x plus 3. And x will go from 0 to 6. So we're just integrating over the xy plane. And let's see here. Integral from 0 to 6. Integral from 0 to negative 1/2 x plus 3. I'm going to do 2 steps at once here. I'm going to do that integral dy. That would be x squared y plus 1/3 y cubed from 0 to negative 1/2 x plus 3. And then let's see what this would be. This would be 1/9 plus 4/9 is 5/9 plus 9/9 is 14/9. And then we have dx there. Oh boy. I think I might skip all of this work. Don't really want to do all of this. It would be, let's see, x squared times negative 1/2 x plus 3. I guess I could put that, let's put that square root of 14/3 out in front. That's 14, yeah, that was 14/9, right? Yep, plus 1/3 times negative 1/2 x plus 3 cubed dx. I don't really want to do that. We'll just say that we did maple. And I actually have the answer written down here. So not really worth doing a long polynomial integral by hand there. So we get 45 square root of 5 over 2 would be the mass. We don't have units here, but that would be the mass of that lamina. Lamina again is like a thickness. It's just like a plate kind of. Okay. All right, next topic here. What if we have a vector field? Can we talk about a surface integral of a vector field and what that would mean? Before we can do that, we have to talk about whether a surface is orientable. Does it have like an outward direction? So here's a famous non-orientable surface, the Mobius strip. If you kind of imagine yourself walking around on it, wait, hold on. Now you're actually on the other side. There's no outside to this strip. There's all one side. You can keep walking around, you end up back where you started, so that's not good. So that's not orientable. Closed surfaces like spheres are outward orientable. Let's see here. So those usually we're going to have usually we're going to talk about spheres or some kind of closed surface that wraps around itself. Okay, so how does this wrap into a surface integral? The most common one is a flux integral. Basically, you have a surface and you have some fluid or some field, and how much of the field is flowing across the surface. So it's a flux integral over that surface. So suppose you have some vector field, and we have just this single component here is this v vector. What we want to do is we want to add up all of the components of the field that are normal to the surface. We want the components of the field that are normal to S. Well, then they would be parallel to a normal vector. Now, we usually use a lowercase n. This is from, I copied this visual from an open source textbook there. So we usually use a lowercase n. So the components of the field that are normal to S will be parallel to n, that normal vector. And so if we want to do that, if we want to find the component of the vector field that is perpendicular normal to the surface, well, that would be the field dot product with that normal vector. And then what we would do is we would multiply that by that area, the area of that representative piece. So the sum, adding all of those up, would be the surface integral of f dot n ds. Okay, one problem here. We need a normal vector to a surface. We need a normal vector to a surface. Well, if you recall before, we had parameterized these surfaces and gotten a tangent vector in the u direction. Oops. Tangent vector in the u direction and a tangent vector in the v direction. And so a normal vector could be their cross product. So let's use, and we'll make it a unit, we need a unit normal vector. We need a unit normal vector. So it would be the cross product of these two divided by their magnitude. Divided by its magnitude, I should say. The cross product is a thing. Okay, well, let's look at what that surface integral, that surface flux integral becomes. So just substituting in that unit normal vector that we found. Now ds, we did this before, you can check your derivation there. That is the magnitude of that cross product, dA. And so interestingly, what happens is, oops, this shouldn't be the double integral of over the surface. This should be the double integral over the region, because now we've parameterized it, right? This is all in terms of u and v, so we've parameterized it. So it should be a double integral over the region in the uv plane. And so you can see the magnitudes there are going to simplify. So the flux integral is the double integral over the region in the uv plane of the field, the dot product with the cross product of tu and tv, and then dA, again in the uv plane. So that is the derivation of what a surface integral over a vector field is. Let's fill in this box here. Surface integral of a vector field. Suppose F, capital F, is a continuous vector field containing a smooth oriented surface. If S is defined parametrically, just like we had talked about before, so it's parametrically defined, then the surface integral of F dot n ds is the double integral over the region R, f dot the cross product of tu and tv dA. One thing here that's important, the direction of the normal vector is consistent with the orientation of S. So we will always have a specified orientation, and typically we're going to have like spheres and they're going to be oriented outward. That cross product should be consistent with that. So sometimes you have to be a little bit careful making sure you're doing the cross product in the right direction. I feel like there are a couple of examples where that comes up. If you have an explicit one where z is a function of x and y, you can do that same analysis we did at the beginning of this video. Where the cross product becomes negative z with the derivative with respect to x, negative z derivative with respect to y, and positive 1 dA. And that's in the xy plane then. So I think that's actually the example we're going to do here. Find the flux of this field through this particular surface, the first octant portion. So we have a three-dimensional field, and we're going to try to find the flux through that plane. All right, let's draw the plane. This is again just the first octant portion. And let's see here, when x and y are 0, z is 8. When y is 0 and z is 0, x would be 4. And then when x is 0 and z is 0, y would be 2. Another one of these like triangle, just the first octant portion of that. That is our surface S. We can easily here get the derivative of z with respect to x. It's already given to us, z as a function of x and y. And then the partial derivative of z with respect to y would be negative 4. Let's take a look at the region in the xy plane. We have 2, 4, and there's our curve. Y will be negative 1/2 x plus 2. Y-intercept is 2, slope is negative 1/2. So this is our region R in the xy plane. All right, so our flux F dot n ds will be equal to double integral over the region of f dot, because this one we do have z given to us explicitly as a function of x and y. Okay, what do we have here? 2y, comma 3, comma negative x, dot product with negative 2, negative 4, 1. And let's just do dy dx again. Sorry, blocking that. Scroll up. Y will go from 0 up to the line, so 0 to negative 1/2 x plus 2, and then x will go from 0 to 4. And I think I might cheat a little bit here and kind of simplify this and then just kind of give you the answer. We don't need to take a whole video just doing a double integral. We did the hard part here. Let's see here. We'll have negative 4y minus 12 minus x dy dx. Why do I have plus 12 written in my work? Oh, because I went a little too quickly here. Partial derivative of z with respect to x and y, those are already negative. Aha. So these should be positive here. Positive, so we'll just kind of cheat and erase. So 4y, positive 4y plus 12 minus x. Good thing I checked my notes. So that's a pretty easy double integral. I'll let you do that on your own time. You should end up with 160/3. Okay, this video is already coming up on 20 minutes. We have one last example. This is a little bit of a lengthy one. But it's a good application of a flux integral. So here we have our field, 2x, 2y, z, represents a velocity field of a fluid. Right? This is the velocity of the fluid. Here's the density of that fluid, 80 kilograms per cubic meter. We're going to let S be the hemisphere with z less than or equal to 0 oriented outward. So what that is, that's the bottom half of that hemisphere, right? Less than or equal to 9, so we have radius 3. That would be negative 3. So we have the bottom half of a hemisphere, radius 3. And we have this vector field, and if we drew that vector three-dimensionally, it would be pointing down, negative x values, negative y values, if we had negative z values, just focusing on negative z values. If z is negative, it's pointing down, and so the vector field is kind of flowing through this surface, like a screen or some kind of surface. It's flowing across that surface. We want to find the mass flow rate. Well, the mass flow rate will be the mass density, which is kilograms per meter cubed, times the flow rate, which will be meter cubed meters per second, will be per second, because our velocity field is meters per second. So it'll be meters per second. So if you multiply those two, you can see you'll get kilograms per second, the mass flow rate. Now the flow rate is actually the flux. That's how we will calculate the flow rate. That's why it's in this section. And the flux, again, is the double integral over the surface of f dot n ds. And here we cannot, well, I guess we could solve for z as a function of x and y, get the bottom half of the hemisphere. We're not going to do that. So this will be, maybe it'd be, I don't know if that'd be better or worse. But we're going to do it parametrically. This will be over the region. And then we'll have our f dot product with the cross product of tu and tv dA. And that's in the UV plane. And the f here is going to be our, actually we could just put in it's our velocity field. Okay, we need a parametric definition of a sphere, and we have it. I think it's example 5. Sorry, scrolling up here. Sphere. Sphere. So we can use that again. It's basically spherical coordinates. So it'd be 3, because ours is radius 3, sine u, cosine v, where we're here, we're using u equals phi and v equals theta from spherical coordinates. So 3 sine u cosine v, 3 sine u sine v, and 3 cosine u. Now we want the bottom half, so we're going to take our phi angle and have it go from pi over 2 to pi. So that'll start at the xy plane and then sweep down to the z-axis. But theta does go all the way around, so v will go all the way to 2 pi. So that'll be our region then. Our region will be, once we get our du, or dv, du, I guess, or du, dv, in whatever order you want to do it in, but it'd be pi over 2 to pi, and 0 to 2 pi. That's going to be our rectangular region in the UV plane. So now we have to find, I think we did some of this already actually, tu cross product with tv. We should be able to go back and use some of the results from example 3. Where did it go? It's right here. So ours will be, I feel like I need to copy this. I'm just going to write it down. I have it here. So let me just write down. I have it written down. This will be 9 sine squared u cosine v and 9 sine squared u sine v. and 9 cosine u sine u. That does not seem right. Cosine u sine u. Sorry, wasting time scrolling back and forth here. I feel like that was the one that we caught. Yep, it is sine u cosine u. Okay, all right. Okay, let's get our vector field v. Kind of confusing using v for two different purposes here. But that's our velocity field is 2x, 2y, and z. So on the surface, that'll be 2 times x, so 6 sine u cosine v. And then 2y, 6 sine u sine v. And z, 3 cosine u. Okay, now I have to find the dot product of those two. Ooh. This is a really long video. I apologize. I should have done this. I should have done this example as its own video. Okay, so dot product with the x is 54 sine cubed u cosine squared v. Hopefully we'll be able to factor some stuff out here. 54. Okay, 50. That's good. Sine cubed u sine squared v. Okay, excellent. That's actually really good. Plus 27 sine u cosine squared u. Okay, well this is great. So the first two you can see we can factor out of 54 sine cubed u. We get cosine squared v plus sine squared v. That's 1. So we get 54 sine cubed u. And then we have 27 sine u cosine squared u. I think from here, boy, we could do some simplifying. I do have some trig identities that I used here to help simplify this to get it to something we could integrate. Boy, I'm not sure how valuable this is to do. So if you do a trig substitution here and you take one of, the only reason why you need to do this is so you can do the integral by hand. And if you do that simplifying, what you end up with after some work is 54 sine u minus 27 cosine squared u sine u. And the only reason why you need to do that is to make the integral palatable by hand. And so I don't know how valuable that is for us to do. So the flux, the total flux, will be the integral over the region. That's pi over 2 to pi, 0 to 2 pi of 54 sine u minus 27 cosine squared u sine u du dv. So I'll let you try that integral on your own. That's worthwhile. It's like 3 or 4 steps. You need a u substitution for the second integral. You might be able to do that one mentally. But you should end up with 90 pi cubic meters per second. So that's the flow, that's how much fluid is flowing through this hemisphere in a given second, 90 pi cubic meters. The units here are big, right? This isn't like a little filter in your kitchen, right? This is a 3 meter wide hemisphere. So it's very big. So that means the mass flow rate will be 80 kilograms per meter cubed times 90 pi cubic meters per second. So you get 7,200 pi kilograms per second. That's a lot. That's a lot. All right, so that is it for this video. We went super long and we skipped a bunch of steps to kind of let you try those on your own. This example obviously is one that's very lengthy. It wouldn't be an exam level one, but it's really valuable for us to see, okay, how are these surface integrals applied? Like, what is the point of a surface integral of a vector field? And one of the main applications for a surface integral of a vector field is the flow, the flux across the surface. What is that flow rate across the surface? That's a very, very common application of this. So that's it for this video. Just 2 more sections left. Shoot 2 short videos, shorter than this videos, and then that'll be it for the semester.